Welcome to a new test and teardown video. This time it's another homebrew project. This is of course a DC power supply, and I really like the design. It is absolutely beautiful. Everything here is nice and straight and really well planned. I think I've seen those meters before somewhere. I can't remember what type of meter that was. And I think they took out the scales and made their own scales. Funny enough, one here is a little bit different color. That cannot be on purpose. And then this case is nice. You untie these and then you can change the angle and all that kind of stuff. And it's very heavy. And here at the back, a quite large power supply with 4 3055s. I mean, really? 4? That is a little bit. I mean, for this type of, look at the size here. Okay. Really? And then 4? That is a little bit like overdoing it, if you ask me, but let's try and see if we can figure out how to open this. It's probably those screws here, right? And then we can pull it apart. Now we know why it's so heavy. We've got 3 transformers in here. 2 very big ones and a small one. It is really, really heavy. And a very large circuit board. And this is definitely some DIY. See? He gave up figuring out how to solve the mechanical mount here, see? Well, how about you measure and think twice before you drill? Just a little clue. It's just really, really funny the way that this is mounted. And also the distance, the clearance distance as well. I think I'll have to fix some of these little issues. There isn't any names or any labels on this board, but I think this is from a magazine because I think I've seen this layout before. So the label here on the transformer is 30, 27, 24, 21, and 0 volts. That will be all the outputs that's down there. And top here is, of course, the input, 220 volts. So this also tells us this is quite old. See, 1.3 amps, and the other one is exactly the same. So it can never be more than 2.6, right? Because you got 2 of these. This is the auxiliary power supply. And that one is 2 times 12 volts in series. So that will be the red wires there. And they go to that tiny little rectifier down here, the auxiliary voltages. And here is the big rectifier for the main output. The big white one here in the middle. And look at the mechanical constructions. Yeah, a lot had to be done. Removing the aluminium parts here to make room for everything. He really tried to put as much as possible into the smallest possible case. And that's also why this is a really, really sexy design. You know, big meters and the knobs and all that. And it is really small and very, very heavy. So I kind of like that you try to build compact. All that is good, but it's difficult when you don't have the skill level to achieve this in a really, really nice way. Some little, yeah, there's a nice plastic Teflon insert here, this white one here. And then the nut, I don't know if that is super safe. So mains goes in to a switch down here, and it turns off both of them, so all that is fine. But then the wires just goes to both of the transformers, and that's it. No fuses whatsoever. I don't think I found a fuse in this unit yet. So that is not so good, because of course something can go wrong. The most likely to happen is a short in the rectifier, or short in the series regulators or stuff like that. But you definitely want a fuse on the primary side of your mains. So that is not so good. And okay, they soldered the wires to that one is loose, but that doesn't matter. They soldered, and then the output is tied to mains. So why would you do that? You never want to tie mains to anything related to output, because you have a feedback loop and you have high gain, and you want isolation from mains to your AC output, your rectifier currents, and then you want your nice clean output to be far away from anything like that. So it's definitely not a very experienced builder. I can also tell you that the ICs, I found a few ICs here, and it's this one is 88, the date code on that op amp, and the other one here is 84. So we can conclude this one was maybe changed, but it's between 84 and 88 at least. That is my best guess so far. Yeah, I think I'm ready to kind of power it up. I mean, what can happen? A lot of things can happen with this type of design, right? It's a little bit spaghetti and stuff like that. Oh yeah, I wanted to show you another little thing here. See all the wires to the circuit board? That's actually a connector, so you can pull the wire, and they use this for all of them, right? But look at those in... how can we get this damn thing to focus? The ones down... Yeah, come on. Can you see they're touching? And this is how good I am with my visual inspection. Here you go in the middle of the picture. You can see they're touching. I really want to see all these problems, because this can of course create a little spark and a little... See? Here we go. Okay, let's proceed. When I started my work on this power supply yesterday, I took a few pictures of the circuit board and the power supply, and I posted some questions into my local Facebook group about electronics, design and construction stuff. And the reason for doing this was really because when I was looking at the circuit board, it looked a little bit familiar. I had the idea it was definitely from a magazine or a book or something like that. I just couldn't name it, and I didn't see any names or numbers or anything at all. But 20 minutes later, I got a hit. One of the users from that Facebook group came with an answer, not like a I guess this or I guess that. No, it was this is in fact the Elektor precision power supply from December 1982. So now we know exactly what it is. And a few minutes later, we got all sorts of links to the PDF files with the full documentation, circuit diagrams and everything. Even links to other people who built this particular power supply. So we're definitely in with all the documentation available. Fantastic. Also, I want to show you a web page where you can see another dude who made exactly this power supply. Of course, he's not super skilled or anything like that. This is just a regular beginner's project. So obviously, people with a lot of skill is not super impressed or anything like that. But you can actually build this and get it up and running and working. And this is what most people find like this is enough. So here you go. You can see the picture of the build. And if I scroll a little bit more down on the page, you can see a few more pictures. Shows the heat sink and the PCB in the case and all that kind of stuff. And later that day, I got this picture. And this is a guy, another local Danish dude called Peter. He's actually from this web page called peel.dk that I often refer to, because he's the guy that collects, scan and distribute all sorts of manuals and schematics and all sorts of that, just like a little side hobby of his. But he made this power supply you see here on the picture with his bare hands. It is, if you look closely, exactly the same circuit board from Elektor, but his skills in mechanical construction, wires and everything here is definitely top class. And he even says the case, the cabinet, is 100% homemade as well. So I must say I am a little bit impressed. So now we have seen both ends of the scale, so to speak. And so let this be the goal for your next do-it-yourself kind of stuff. If you can build like Peter, I would be very, very happy about your level. Instead of going through the entire documentation, schematics and all that kind of stuff, I will just put a link in the description to the Peel site where you can find a snip from the Elektor magazine. And there you will find, of course, the full documentation. But I just really want to show real fast the schematic from that documentation, just so you can see the little tricks that I have done here. So this is first the original schematic, and this is, as you can see, made for 3 3055 transistors, and they have, of course, those 4 resistors on their circuit board. Also, on this schematic, you'll see the left bottom rectifier bridge that is also located on their circuit board, and that is definitely not what you want to do, because it's gonna burn itself way too hard. And to the right of C12, that capacitor goes on the front panel banana jacks. In parallel with that capacitor, there is a reverse diode missing, and you want to have a reverse diode in case you experiment with serious connected power supplies and one of them goes into current limits. I mean, or you turn them on and off not at exactly the same time and all that kind of stuff. So definitely you need a reverse diode. And here I want to show you the schematic of my modified and improved version. I use, of course, the 4 3055 transistors, and I couldn't redo the circuit board layout and all that. So of course I had to use the 4 positions on that circuit board for my 4 emitter resistors. So what I had to do was to put the 4 local loading resistors of the driver to the 4 base inputs to the 4 transistors. Those 4 times 220 ohms, they are now located at the heatsink. So this is a little bit simpler and easier design, to be honest. This is definitely how I would have done it. So now you have both of the schematics. So I've been playing a little bit. So this is 20 volts. And let me give it 2 amps. So the amp meter is showing a little bit too little. Anyway, so this is 42 watts of output, 2 amps and 21 volts. Okay, so power consumption on input is 97 watts. All right, so where is the rest going? Yeah, the 42 that I deliver out here, but the rest is heat in the transformers, rectifier, and the heatsink, the series regulator. But there's something I really need you to see. This is the rear side, and of course I just painted all the 4 power transistors with some black ink, because this way the thermal camera will work. So far, as you can see here, it's only 35, and everything is more or less the same temperature. All right, so now while we are looking at this picture here, I will turn on the load. So this is 2 amps, and I'll try and hold the camera, or maybe I can hold it like this. So what is going on here? As you can see, the top transistor here goes really, really warm. That one here at the top goes really warm. And this one goes ice cold. See, I can probably touch this one without any problems, but this one will burn my fingers. So why is this happening? Is this the driver? I don't think so, because up here is a transistor driver, or is it down here? There's a, yeah, I think it's, I can't really remember. I just looked, and there's another little transistor here at the back. So I think this is a very good example of thermal runaway of paralleled transistors without emitter resistors. I mean, this is definitely bad design. There's something here that is not supposed to be like that, right? So all the power go in one of them, and then a little bit, and then nothing. I mean, this is not how you should do it. And I'll try and see if I can figure out what is going on. Let's take off the heatsink and see what is the circuit behind that, the power transistors here, right? I think I found one of the reasons for the 4 3055s not being equally warm. First of all, one of them was ice cold. So let's start by looking at the yellow and red wire here, right? See, I think I found why. So, and then the other 3 emitter wires, they go to 3 different emitter resistors. They are down here. I think we got 3 or 4 of them right there. And then we got another one down there. This is the output sense resistor. And I believe it's measuring the voltage across this resistor and using this potentiometer to display the current on one of the meters. The other meter is most likely voltage measurement, and it goes, of course, to the other meter. So far, so good. But the resistors, they're only 0.22 ohms, why would you use such a low value? Because the output current here is quite low, and that is a bad idea, because this way you do not correctly feedback the current, and current sharing is not enough for the difference in those transistors. So of course you want to have as high as possible emitter resistor as you can afford, voltage drop wise and power loss wise. But look at those big resistors that are like 5 watts, and the output is only 2 amps. So something here is completely wrong. If you do the math here, you can see those resistors are wrongly chosen for the job. Let's look a little bit more on the backside of the circuit board. See, I just explained about the emitter resistors. Let's try and follow this track. Here is the output current sense resistor, and this is of course the output, right? I think here is one emitter resistor, here is the other one, number 3 and number 4. So I think we have 4 resistors, but for some reason it's not implemented correctly, and one of them is looking a lot different than the others. So maybe there's a very different value in one of them, and this way one of the 3 that is actually connected is delivering all the power, and the last 2 is not that much, and the last one is not connected. I mean, that is my theory so far. We got a few other problems that I definitely have to fix in this power supply as well, but this is just my first little go-to. Let's of course share the currents correctly, rewire everything so it's more neatly done and not all this mess. And yeah, let's see what we can do for this. I can show you a little bit more about this power supply. See, here we go with the 4 resistors I talked about. That will be the 3 emitter resistors, and that one here is a 10 ohm resistor, and those are all 0.22 ohms. Okay, so here on the heatsink there is a driver. The white wire here goes from the op amp system. So this one is also an emitter follower. See, it's where are we? Its collector input is also connected to all the other collectors. So that is our positive high voltage, and the output, the emitter from this driver, drives all the base signals here for the 4 output transistors. That red wire here is a base load. So that is the 10 ohm resistor I just talked about. And it goes, of course, to the output. That means the emitters, after the emitter resistors. So what we could do is we can remove this wire here. We don't need that. And then we can put the resistors, instead of having one 10 ohm resistor, we can have 4 resistors from base to emitter on each of these, and that will load the base drive signal down. You need to load the base drive down, otherwise you can have an unstable emitter. This is a Darlington or a pre-driver, right? So if you don't load the base to the output stage down to the emitter or to the output, you will have an unstable system, because it can only do positive, it cannot do negative, and it must be stable at a higher frequency domain as well, right? So that is what I want to do, because I want to remove this wire, because I want to use the space on the circuit board. I want to remove this 10 ohm resistor and put in 4 emitter resistors here, and instead of 0.22 ohms, which is of course not enough, I want to add in 2 ohm resistors, a little bit bigger, but I will be able to fit these 4 resistors here, and then I will have equal current share. And this is a gift that just keeps giving. So of course, yeah, that is my new resistors. But I just keep finding other things that I want to deal with. Those wires, by the way, they're really, really thick and annoying. So I want to replace them because it's only 0.6 amp per output. So we don't need all those thick wires to make everything much more annoying. And look at that one. This is a black wire. It is connected to the main capacitor positive. This don't really help with debugging later on, right? So this one, I want it to be actually anything but black, by the way. See, black wire is all the collectors. That we cannot have. And there's another fault. Look at the pre-driver here. It's directly mounted to chassis. So that means we have positive voltage on this chassis. Yeah, it's actually on the entire chassis. We have positive unregulated main voltage. So whatever happens when you have a circuit on your desk and you touch this metal here, you have a positive high voltage of like 35 volts or something like that. That's not good. And also, this prevents you from correctly grounding this power supply because you want, of course, a correctly protected, grounded mains entry, right? You cannot have stuff like this without the chassis being correctly grounded to earth for your own protection. I mean, really? To do the cleanup of the power supply, the heat sink part of it. Now this transistor here is isolated. The distance to the side here wasn't really good, so I added a little bit of varnish here. And now I'm looking at the different solder jobs here, and I want to show you something. See, I tried to cut this so I could solder it a little bit better, but look, I can move this. It's not soldered. And I think it's the same with this one. I don't know if I can. I think this explains why we got some hot and some cold transistors. I mean, this, of course, is not working. So I am done with the first modifications. My transistors should work. All my cables, they are nice and fine here. Also, this auxiliary supply, that will be the thin wires here. They are, of course, twisted to that auxiliary transformer, and all the other AC wires, they are now twisted. And yeah, this is the output wires. I just fixed that as well, the blue and the red one. Now I will just test if my transistors and all that cooling and stuff is okay. And then I want to fix all this wire madness here and fix them unstable voltage behavior and create the correct voltage sense point at the banana terminals, because that is of course what we want. So let's do this exactly the same way as yesterday. Everything here is nice and cold. And I will just turn on the load. That it will be 2 amps. And now I will double check the temperatures of all 4 transistors. I really hope. Yeah, I really hope they're gonna be more or less the same. Depending on the angle here, you see. Or also, how much paint did I put on? So I think we should normally not wait that long because we should see something. But it's definitely a lot better, right? They also, oh yeah, of course they run colder because now we have current in all of them, right? So if we take this, it's 40. I mean, this is so close to 40. Okay, and 38. I think problem is 39, right? So I think my problem with the temperature is solved. There's probably a reason why it's a little bit warmer in this end. I don't know. Let's try and see if we can make some photos about that. See, this is the two power transformers. Of course, they get a little bit warm. And the circuit board, we got current sense resistor in this area right there, right? That is the one all the power goes through. And up here we got all my 4 emitter resistors, and they are, of course, share the power more or less equally. But look at that. This is the rectifier bridge. And to no big surprise, that one gets really warm. It is, what? I don't know, I just can't see a goddamn thing. 70 Celsius. And that is not so good because this is only 2 amps. And it has only been running for a few minutes. So it is quite clear that what to do. I feel like this is the never-ending story. But I'm having a lot of fun. So now, well, both meters, they got stock needles. So I need to fix that as well. Meanwhile, I can show a little bit more of all the cool things that I've done. Yeah, I figured out that if I move the front a little bit up here in the top hole, then I can access everything and it's still completely assembled and easy to go. See, now the bulbs there are replaced with LEDs. And yeah, look at that rectifier there. And oh, there's a fuse. And all the wires, they're now nice and clean and I can figure out what is going on. I also added sense. I don't know if you can see the thin wires and the thick wires. So that is main output and sense. Yeah, it's getting there, more or less. But it does really take a long time for me to do all these things. But it's just because I think this is a super cute power supply. So I really like the design, so I think it is worth fixing. And see, all the wires I made for the heatsink, they're now nice and clean and not causing all sorts of confusions. Yeah, the last few wires, see the thick ones here goes to the 2 potentiometers. That is the last thing I want to play with. I also need to fix that as well. But I think that is the very, very last thing I will do. Look at the back of the meter. It's from 1954. So even back in 82 or something, or 85 or whenever this power supply was built, even then, the meters, they would have been taken from something. And I still cannot remember exactly what. I'm super sure that I've seen these meters before, by the way. And to open these, it drives me a little bit nuts. Yeah, nuts. Those tiny little nuts, look at that. And you can barely fit a screwdriver in them, and you need to, move around here, and you only move them a quarter of a turn. This is going to take a half an hour to get those damn nuts off. Those annoying meters. This one I fixed in first go, but this one, I also had it replaced and everything after my first fix, and now it was stuck again. So it's a new problem. Got 2 different stock problems with these meters. So they're driving me a little bit nuts, I must say. First, he mounted this plate here with the washers under the plate. So this scale plate was too close to the needle. And of course it needs to be down there, right? And then, after a while, I don't know if you can see this, but the end of the needle bend, right there, that goes down there, actually hit sometimes this little piece right there that is going to the little adjuster spring. So now I've been bending a little bit around here and trying not to screw up this unit. And now I hope I can put back this meter for the last time. And then I will be done. So last night I left this unit on, and today, after work time, it is still 30.00. I mean, the long-term stability is also good. So I think I'm done playing with this unit and repairing it and improving it and all that kind of stuff. And it is really good, this reference chip they're using. I also wanted to show you what else I have done of modifications. Let's see if I can get a little bit of light here. Can you see the big potentiometer here? So now this is my voltage potentiometer, that big bad boy here. And this is of course a really good 10-turn potentiometer, but this also means I couldn't use the original knobs because 6.3 millimeters and 6.0, oh no, it's a classic problem. So I replaced both the knobs, so now that works. I also also swapped the wires for the current set potentiometer because look, of course you have to dial it down and then it goes to current limit, right? Clearly. And I adjusted the brightness of the lamps so they are more or less the same brightness. So I wanted to show you the output voltage versus load, and now you can see the load is 0. And let's just try and enable 1 amp. See, this is what happens when you're using a local sense here on the back side. I'm not even sensing on the front. Well, I don't know, you can probably see what I'm doing here. I got a very big, good banana. This is a very good quality banana that can handle a lot of current. And this is the point where I pull the current, and this is where I measure the voltage. Of course, not at the same point. And this is how you can make it. This is how you can reveal how good it is really at this point of your power supply. So this is 1 amp. Let's crank it up to 2 amps. Oh, not 1 amp and 1 milliamp. 2 amps like that. And then we just go on and on with 2 amps. And this is fully on. Good. So let's see what can this power supply do. I think it can actually do 3. Then it drops a little bit. Okay, so let's go a little bit down. Okay, here 2.7, 2.6, 2.5, and then it is perfectly stable up to 2.5. Somebody said, how about overshoot and how about the regulation and all that kind of stuff? So this is the spot where I just proved that this power supply should be stable, as you can see here, right? So let's look at the scope like I just did here and then zoom in all the way. So this is 200 millivolts per division, and then we can see this little spike when I do a complete load drop from full load to nothing, and then it cranks up about 0.5 volt, and then you see here this is the regulation speed, and then it goes back again. So yes, let's show this again. So this is 2.5 amp, and let's just go down to 2 amp and see how it behaves. Of course, it's a lot better. You can also see the overshoot here. I mean, this is really good for a power supply designed in 1982. I am absolutely happy about this. So this is 1 amp. And then we have, I need to zoom it up so we can see what is going on here. So now this is 100 and 200 millivolts spike. I load drop rise here. So yeah, and then again, of course, to 0. What I can do to fix this is just add a little capacitor on the output and then this problem is gonna go away. But I think we've already talked enough about this power supply. So I think I will say thank you very much for watching, and I hope you had a little bit of fun. Bye bye.